Most of the problems on this worksheet are going to have to do with naming alkanes, although I've got some other problems on there as well. I'm just using this title because it's what corresponds to the relevant section in your textbook. So the first problem that we're looking at here has nothing to do with naming at all. I'm asking you to classify these pairs of molecules. So you've got two molecules here in a box, and I want you to classify them as being either constitutional isomers of each other, or being the same molecule just drawn two different ways. Or perhaps their relationship is neither of those two. So they're not constitutional isomers and they're not the same molecule, they're just something different. As a reminder, constitutional isomers are two molecules that have the same formula. They have the same molecular formula. So this means that they have the same number of carbon atoms, they have the same number of hydrogen atoms, any other atoms that might be present. They have the exact same number of all of the different types of atoms, but the atoms are put together in some sort of different order. So they have the same formula, but they have different connection of atoms in the molecule. So that's what we're looking for if we're looking for constitutional isomers, two molecules that have to have the same formula, but the atoms have to be connected in some sort of different way. Connection. The same molecule, if the two drawings represent the same molecule, that would mean that they would need to have obviously the same formula, and they need to have also the same connection. Now, when we're looking at the connection of the atoms in a molecule, we aren't thinking at all about the way that we draw them, like the left to right versus up and down. So if we have 5 carbon atoms that are connected and drawn horizontally versus 5 carbon atoms that are connected and drawn vertically, those two representations would be of the exact same molecule. So the way that we choose to draw them means nothing when we're comparing the two structures to each other. All that we're looking at really is the order of the atoms in terms of their connectivity. So when we look at these two molecules right here, if we just look at the way that they're drawn, they may look like they're completely different molecules. They might be, they might not be. The first thing that we should do is count up the number of carbon atoms and the number of hydrogen atoms in the molecule, because we need to know if they have the same molecular formula or not. So I'm using dots to show all of the different carbon atoms in these molecules. Remember, there's a carbon atom at the beginning and the ending of every little line there. And on the left-hand side, I come up with 1, 2, 3, 4, 5, 6, 7 carbons. I'm just going to write that underneath. And on the right-hand side, I've come up with 1, 2, 3, 4, 5, 6, 7 carbons. So they have the same number of carbon atoms. What about the hydrogen atoms? On the left side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 hydrogens, and on the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these two molecules do have the exact same molecular formula. That means that they are either constitutional isomers, or they are an identical molecule, the same molecule that's just drawn slightly differently. So how are we going to figure this out? Well, what we need to do now is look at the connection of the atoms in the molecule. How are the atoms connected to each other? In the first molecule, if we want to start with this is a little branch right here. We've got that little branch right there. And if you notice in the second molecule over here, we have a similar little branch, just one carbon atom hanging out all by itself. I'm going to color both of those little carbon atoms pink so we can keep track of them. And I'm going to make the carbon atom that's attached to it, I'm going to make that blue right there. So when we look at the blue carbon atom here in our drawing on the left side, if we continue moving to the right, I'm going to get a different color, then we're going to have 2 carbon atoms that kind of follow that blue. And if we look over here at our second drawing of the molecule, if we're at our blue carbon, and if we also go to the right, we're going to end up with 2 green carbon atoms as well. Going back to our first drawing and going back to the blue carbon, and let me get a different color here. I'm going to use purple. So if I go back to the blue carbon and now I go up, I'm going to have 1, 2, 3 purple carbons. And to my second drawing, if I go back to the blue carbon and I go to the left, then I'm going to have 3 purple carbons. So these two molecules here, they have, not only do they have the same molecular formula, they also have the exact same connection of atoms. They have a pink atom that's connected to a blue, and that blue atom is connected to 2 greens and also connected to 3 purples. It doesn't matter that they're being drawn in different ways. They are identical molecules. That is their relationship. Identical. And this is a pretty tricky concept, so let's practice this again. We've got 2 cyclics over here. Let's begin by identifying the molecular formula. So let's count our carbons. 1, 2, 3, 4, 5, 6, 7. That's a C7. And on the right-hand side, 1, 2, 3, 4, 5, 6, 7. So that's also C7. Now let's count our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. And on the right-hand side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So they're both C7H14. Because they have the exact same molecular formula, this means they're either constitutional isomers or identical molecules like we saw in the first example. So what we need to do now is analyze their connectivity. Now this one is actually easier to see, to compare their connectivity, because for both of these molecules, we have this 5-membered kind of central portion of the molecule. We have that sort of pattern that we can see right away, right off the top of our, right off the bat. We have that similar 5-carbon pattern. And then for the substituents on this molecule, the branches on this molecule, we have 1 carbon sticking out all by itself right there. And then in the molecule on the left-hand side, our second branch is immediately adjacent. So they are attached in positions that are side by side on the molecule. They're side by side on that 5-membered central ring. Whereas the molecule on the right-hand side, these 2 branches, they're not immediately side by side. They're separated by this carbon right here. This means that these 2 molecules have a different connectivity, a different connection of the atoms. Specifically, this branch right here is connected in different places when we compare these 2 molecules. So the relationship between these 2 molecules is that they are constitutional isomers because they have the same formula, but their atoms are connected together in some sort of different way. Let's take a look at our next example here. The first thing we want to do is count up the number of carbons. 1, 2, 3, 4, 5, 6, 7 versus 1, 2, 3, 4, 5, 6, 7. C7 and C7. Let's count our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C7H14 for both of them. Having the same molecular formula means that they are either identical or they are constitutional isomers. Now we want to look at their connectivity. This one's also pretty easy to see. Probably the easiest one. Maybe I should have made this the very first problem on this worksheet. The molecule on the left, we have 6 carbon atoms that are connected together in a ring. And the molecule on the right, we only have 5 carbon atoms that are connected together in a ring. So there's completely different connectivity or connection of carbon atoms. Also, the molecule on the left has only 1 branch. The molecule on the right has 2 branches. So these molecules are constitutional isomers, again, because they have the exact same formula, but they have a different connectivity. Here's our last example. Let's count our carbons. 1, 2, 3, 4, 5, 6, C6 versus 1, 2, 3, 4, 5, 6, C6. And our hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, H14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12. Ooh, so here we're looking at two molecules that have the same number of carbons, but they do not have the same number of hydrogens. They have different molecular formulas. If they have different molecular formulas, obviously they can't be the same molecule. And also, if they have different molecular formulas, they can't be constitutional isomers, because one of the rules to be a constitutional isomer is that you have to have the same molecular formula. So the relationship here is neither constitutional isomers, nor is it identical molecules. These two molecules are just completely different from each other. So they are not identical, and also they are not isomers. They are just two completely and totally different molecules. So now that we've practiced that, and this is actually really relevant to naming molecules, we're going to start working on learning how to name molecules. We're going to begin by learning how to name this molecule right here. There are basically 4 steps that we want to take when we're naming a molecule. The very first thing that we need to do is find the longest carbon chain. So this means we're looking for the longest continuous set of carbon atoms in the molecule. To do this, we want to start at any end, so like this particular end that I'm highlighting, and we want to move to any other end in the molecule. Our eyes, if you're born and raised in America or other countries that have similar reading pattern to us in America, your eyes are naturally going to be drawn from the left-hand side to the right-hand side, because that's the way that we read. So you want to keep in mind that the molecules are not written like a book. They don't necessarily move from left to right. They could move from left and then up, or they could move from the top down, something like that. So you want to consider all possibilities when you're trying to find the longest continuous chain of carbon atoms. I like to start at one end and then just move to the first end that I come to in the molecule and count how many carbons that might be, and then try another option as well. So if I start at this end and I move to the top right here like that, that gave me, that particular order gave me 5 carbon atoms. I'm going to redraw the molecule. So this was 5 carbons. If I start on the left-hand side and then count straight across from left to right, like the way our eyes want to read, that gave me 6 carbons. So that's good. Again, we're looking for the longest set of carbons. There is one more possibility for counting carbons in this molecule, and that would be if we started at this top and we moved our way to the right-hand side. That's only 4 carbons. Now, if you're thinking, wait, there's another way, I could start here and I could go this way, recognize that that's exactly the same as the first one that we did. So whether we're taking that path from left to right or right to left, it's including the same number of carbons. So this set right here that I have drawn, this is our longest chain of carbon atoms, these 6 carbon atoms. And this is what we refer to as the parent chain. Once we have found our parent chain, and I'm going to be working with this drawing, we're going to number that chain starting at the end closest to the substituent. The substituent is just a fancy way to say branch. So we want to start at either this end or this end, whichever end is closest to our branch. For us, we want to start over here on the right-hand side, and we want to number that carbon chain. So we're going to number our carbons 1, 2, 3, 4, 5, 6. These numbers that we use on the carbon chain are going to help us identify the location of the branches. Next thing that we want to do is locate the substituent. By that it means what carbon atom is it on. Our substituent, the way we numbered it, our branch, is on carbon number 3. And then we want to name our substituent. So you're probably going to want to reference the video that I've posted where I give you the names of all of the branches and the names of all the parent chains. A 1 carbon branch, which is what we have here, a 1 carbon branch is named methyl. And again, the names of all of these branches are covered in a previous video. Then the next thing that you want to do, we're going to put the substituent in front of the parent chain. So the next thing we want to do is name the parent chain. A 6-carbon parent chain is called hexane. And again, the names of the parent chains are in a video all by themselves, so you're going to want to refer back to that video for these names. And that's all that we have to do. That is the name of this molecule. Now, trust me, it does get easier with some practice. So that's what we're going to continue to work on this worksheet. We'll practice it a little bit more. What about if we have more than one substituent or more than one branch in a molecule? In that case, we're still going to follow these same general rules, find the longest carbon chain and number it, starting at the end closest to the very first branch. Locate and name the branches, etc. The one thing that we want to pay attention to when we're actually putting the molecule's name together is that the substituents or the branches are put in alphabetical order at the beginning of the name, not numerical order. It would be logical to put them in numerical order, but that's not how we do it. We alphabetize them. So let's take a look at this very first example that I have here, and the name is already set for us. The longest parent chain goes like this, from left to right for that molecule. And if we numbered this parent chain, following the rule, we want to number at the end starting closest to the first branch. So that means we want to number it from right to left, from right to left. That means that our branches are on carbon number 3 and also on carbon number 2. The branch that's on carbon number 2 is a 1-carbon branch, and that guy's name is methyl. The branch that's on carbon number 3 is a bromine, and that guy's name is bromo. Again, all of these names are covered in previous videos. So when we're putting the molecule's name together, we don't name our branches in number order, number 2 and number 3. We name them in alphabetical order, B, which comes first in the alphabet, and then M, which comes second. So this molecule's name is 3-bromo-2-methyl-hexane. When we're naming these molecules, we always use a dash to separate a number from a letter. So if we have numbers versus letters in the names, we always want to use a dash to separate the numbers and the letters. Let's try practicing with our next example over here. First thing that we have to do is find the longest chain of carbons. We could start at any one of these ending points, and we just want to count to another ending point. So if I start here and I count 1, 2, 3, 4, 5, 6. If I count to this end, 1, 2, 3, 4, 5, 6. So it's a tie, and that happens quite a bit. If it's a tie, you just pick one, whichever one. It's not going to make a difference. I'm going to go with this one. We do have another possible branch like this. That's only 3 carbons, though. That's definitely not our longest. So I'm going to go with this being our longest chain of carbons, like that. And we want to number that chain starting at the end closest to the first branch. So here's our 2 ends. So we want to start on this end because it's closest to our first branch. 1, 2, 3, 4, 5, 6. We want to locate and name our branches. This branch right here is located on carbon number 3, and its name is chloro. This guy right here is located on carbon number 2, and its name is methyl. When we put all of these together, we want to alphabetize those 2 branches, not put them in numerical order. So I'm going to put the chloro first and then the methyl second because I'm alphabetizing chloro versus methyl. 3-chloro, and remember to use a dash to separate your numbers and your letters, 2-methyl, and then once I get the branches named, I'm going to name the parent chain, 6-carbon chain, which is, if you look back at your notes, that is hexane. We've got one more example over here where we can practice. We want to first find the longest carbon chain. So I'm going to start here. If I go this way, that's only 3. That's not very good. 1, 2, 3, 4, 5. That's better. 1, 2, 3, 4, 5, 6. That's really good. But I still want to check my other options. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There's a tie, 6 versus 6. Let's keep checking our options. 1, 2, 3, 4, 5, 6. That's another 6. So we've got 3 ways that we could do this with 6 carbons. I'm just going to pick this one right here. We want to number this carbon chain starting at the end that's closest to our branches, which is on the left-hand side. So we're going to number it from left to right, 1, 2, 3, 4, 5, 6. Now we want to locate and name these branches. First branch is on carbon number 2, and it's a 1-carbon branch, which is a methyl. Our next branch, this guy right here, on carbon number 3, this is a 2-carbon branch. This guy's name is ethyl. We're going to put these 2 branches at the beginning of the molecule's name, and we're going to put them in alphabetical order. So that means that the ethyl comes first, 3-ethyl, and then the methyl comes next, 2-methyl, and then we name our parent chain, which is a 6-carbon chain, which is hexane. Let's see what else we have over here. Now we're looking again at having 2 substituents, but this time the 2 substituents are identical to each other. If we have 2 identical substituents, we don't have to repeat their name. We don't have to say methyl-methyl. We can just use the prefix di, which is used to indicate that there are 2. So let's look at this very first example. For this first example, here's our longest parent chain. It's a hexane. We have a methyl on carbon number 3 and a methyl on carbon number 4. Instead of saying 3-methyl, 4-methyl, hexane, we can say 3,4-dimethyl. That means 2 methyls, hexane. Notice that we're using a comma to separate the 3 and the 4. So when we have a number and a number back to back in a molecule's name, we always separate those 2 numbers with a comma. Number versus letter, we use a dash. Let's take a look at these other 2 examples. First molecule here, we have a 3-carbon parent chain. We want to number this from left to right. We have a chlorine on carbon number 1. We have a chlorine on carbon number 2. So we can say 1, 2 dichloro instead of saying 1 chloro, 2 chloro. And then we follow that up with the parent chain, propane. 3-carbon is propane. And then we have one more example over here. This is our parent chain. This time we're going to be numbering from right to left. Remember, we want to start numbering on the side that's closest to our first branch. Our branches here are bromines. We have 2 of them. We have a bromine on carbon number 2 and a bromine on carbon number 3. So we can say 2, 3 dibromo. A 4-carbon molecule is pentane. Last thing that we're going to look at here is naming cycloalkanes. So these are molecules where the carbons are connected to each other in a ring instead of in a straight chain. When you have a cycloalkane, you get to pick where to start your numbering. So you get to pick which carbon is carbon number 1. And you're going to choose the carbon that is holding the branch. So for this very first example right here, we're going to choose this carbon right here to be carbon number 1, and then we'll just go around the ring. Sometimes we go clockwise, sometimes we go counterclockwise. We'll look at that in the next set of examples. So we're going to number, because there isn't an actual ending like with our straight chain, we don't have an end because it's a cyclic. We have to choose who to call carbon number 1, and we're going to put the carbon number 1 position is going to be the one that holds the branch. Now, because of this rule, because we're choosing which carbon is carbon number 1, we don't say 1 in the name of the molecule. So when it comes time for us to name this molecule, we say we have a branch, it's a methyl, and it's located on carbon number 1, but we don't say 1 in the molecule's name. It is implied that that branch is going to be on carbon number 1. And in fact, it's incorrect to say 1 in the molecule's name. So this molecule's name, we just jump straight to the name of the branch. Methyl cyclohexane is the parent name. Here is an example that we're going to try over here. This is our 5-carbon ring, our 5-carbon cycloalkane. We have 1 branch, And so that means that the carbon that's holding that branch, that's going to be our carbon number 1. That substituent or that branch is an ethyl. And so that means this molecule's name is ethyl cyclopentane. Again, we don't say 1 because the 1 is implied. This is only the case for cyclic molecules. The 1 is never implied on a straight chain molecule. Last but not least here, if we have a cycloalkane that has more than one substituent or more than one branch, this is a little bit trickier. In this situation, we're going to start by putting the substituents in alphabetical order. So the first thing we're going to do is alphabetize them. And then once we get them alphabetically ordered, the first substituent in the name, the one that comes first alphabetically, will be on carbon number 1. So the first alphabetically, that's the one that becomes carbon number 1. Let's look at this example right here. So here we have a 6-carbon cyclic, and we have 2 substituents. We have a methyl, and our other substituent or branch is an ethyl. So now we look alphabetically, which one of these 2 comes first in the alphabet. Ethyl comes first in the alphabet, so that means that this guy gets carbon number 1. Now, once we've decided that this is carbon number 1, we're going to number either clockwise or counterclockwise, whichever direction gets us to the other substituent the fastest. So if we go counterclockwise, we're going to get to the methyl group right away. If we continued clockwise, it would take us quite a while to get back around to the methyl group. So our goal here is just to get to the other substituent as fast as possible. And this gives us the name 1-ethyl, 2-methyl cyclohexane. Here, in this case, the 1 is not implied. You definitely have to include that in the molecule's name. Let's try that over here with this example right here. We have a 5-carbon cyclic. We have 2 substituents. We have a bromo, and we have a chloro. When we alphabetize them, bromo versus chloro, bromo comes first in the alphabet, so it's going to be carbon number 1. Now, which way should we go, clockwise or counterclockwise? We want to get to the chloro as fast as possible, which means we want to go counterclockwise to number this. This molecule's name will be 1-bromo. Our chloro ended up on carbon number 3, 3-chloro, cyclopentane. Now, the last thing that I have on this worksheet is to go back to the very beginning where we were doing the constitutional isomers versus identical and name all of those molecules. And so this video is getting pretty long, so I am going to go back to the beginning of the worksheet, but I'm going to name those molecules really, really fast. So maybe what would be cool to do is like pause the video and see if you can name these molecules on your own and then come back to the video and see how you did, because like I said, I'm just going to plow through these names really quickly. So for this first set of molecules, these molecules are identical to each other, which means that they should have the exact same name. For 2 identical molecules, they should have an identical name. This first one that I've come up with, I have a methyl on carbon number 3, so this is 3-methylhexane. And over here, like I said, this better be an identical name. 1, 2, 3, 4, 5, 6, also 3-methylhexane. I'm just going to move that name in the middle. They both have the same name. For the next one, we have cyclopentanes. This is 1,2-dimethyl cyclopentane. And our molecule on the right-hand side is going to be 1,3-dimethyl cyclopentane. One of the ways that you can tell if molecules are identical to each other or not is name them. If they are identical molecules, they will have the same name. This is methyl cyclohexane, and this molecule is right here. I've already named it, 1,2-dimethyl cyclopentane. Next, we have just a plain old alkane, hexane, and also cyclohexane with no branches.